Good morning, friends. In chapter 10 Wave Optics, we are discussing about the MCQ question asked in good set. Already we discussed about the Neet and All India PMD. Now, the next question that is asked in 2015, if the wavelength of the light is 4000 angstrom, then the number of wave in 1 millimeter length, how we can find out how many numbers are already lying in 1 millimeter length. For that purpose, here the equation is that the number of wave n is equal to d upon lambda. D is the length and lambda is the wavelength. Numbers of wave n is equal to d upon lambda. D is given 1 millimeter. That means the 10 is to minus 3 meter. And wavelength lambda is given 4000 angstrom is equal to 4 into 10 is to minus 7 meter. Substitute the value, 10 is to minus 3 upon 4 into 10 is to minus 7. Therefore 1 by 4 into 10 is to 4. 1 by 4.25 into 10 is to 4. That means the 2500 waves of wavelength 4000 angstrom are lying in 1 millimeter length. Again, here the wavelength of the light is given 4000 angstrom. Corresponding to wavelength 4000 angstrom, how many numbers of wave are in 1 millimeter distance or the 1 millimeter length? So equation is that the number of wave in distance d, n is equal to d upon lambda. Distance d is given 1 millimeter, convert into meter, n is to minus 3 meter. Wavelength is given 4000 angstrom, therefore 4 into 10 is to minus 7 meter. Substitute in this equation, 10 is to minus 3 upon 4 into 10 is to minus 7 is equal to 1 by 4 into 10 is to 4. 1 by 4.25 into 10 is to 4, therefore 2500 waves are in 1 millimeter length. Okay. Now next is velocity of electromagnetic waves having wavelength. Lambda is given 5000 angstrom in a medium of refractive index 2 is, we have to find out the velocity of a wavelength of light 5000 angstrom. Refractive index n is given the 2. What should be the velocity v? Now, from the equation of refractive index depends on the velocity. N is equal to c by v. Refractive index is equal to refractive index n is equal to c by v. Therefore, v is equal to c by n. V is equal to c by n. C, velocity of light in a vacuum. Velocity of a light in a vacuum. So is equal to 3 into 10 is to 8 upon refractive index is 2. Therefore 1.5 into 10 is to 8. 3 by 2, 1.5 into 10 is to 8 meter per second. That is our answer. Again, from the definition of the refractive index of a given material, if we know the velocity, at that time we can find out the refractive index of a medium from the velocity like this equation, n is equal to c upon v. C is the velocity of a light in a vacuum and v is the velocity of a light in given medium. The ratio of these two velocities gives the refractive index of a medium with respect to vacuum. Therefore, n is equal to c by v. From this equation, v is equal to c by n. We know that c, velocity of light in vacuum, 3 into 10 is to 8. Refractive index of a material of the medium is given 2. So 3 by 2 into 10 is to 8, that means the 1.5 to 10 is to 8 meter per second. B option is the right. Now in 2016, depends on the theory, the question is asked, a diffraction pattern is formed by blue light. Now, if the blue light is changed by, or replaced by yellow light, what's happened in the result? First option is given, the maxima and minima are broadened and becomes distinct. That means the maxima and minima becomes the white and also separated with each other. Next is, the maxima and minima are narrow and more crowded. Maxima and minima becomes the very small and also very close to each other. C, the pattern does not change. There is the no effect take place in diffraction fringes. And D is diffraction pattern is disappearing. If we change the light yellow from blue, so diffraction pattern is disappeared. That is the fourth option. So which option is right? For that purpose, we know that the diffraction is depends on lambda upon D ratio. Diffraction patterns or the diffraction depends on lambda upon B ratio. Now here we change the blue light is replaced by the yellow. Therefore the wavelength is changed. Therefore diffraction pattern must be changed. Here wavelength of yellow light is greater than the wavelength of blue light. Wavelength of blue light. Therefore, diffraction pattern becomes the more broadened and becomes the distinct. Hence, maxima and minima becomes broadened and distinct. Again, diffraction depends on lambda upon D ratio. Here the D does not change, that means the width of the slit we do not change. Only we change the incident light. Initially the blue light, now we replace the blue light by the yellow light. Therefore, the wavelength of yellow light is greater than the wavelength of blue light. Therefore, lambda is increases. Therefore, the diffraction pattern is more spread. That means the maxima and minima are broadened and distinct. Broadened and distinct. Here this is asked in 2016. Now next is also asked in 2016. In front of a diffraction by a single slit, the width of the slit is 0.01 centimeter. The wavelength of light incident normally on a slit is 5000 angstrom. The angular distance of the second maxima from midline of central maxima is how much radian? Here the width of the slit is given B is equal to 0.01 centimeter. Wavelength of the light used is 5000 angstrom. So what should be the angular distance of second maxima? Theta we have to find out, for the theta 2. For that purpose, the condition for the nth order maxima, condition for nth order maxima, already we know that in diffraction pattern d sin theta is equal to 2n plus 1 into lambda by 2. For n is equal to 2. Here we obtain the d sin theta is equal to 5 lambda by 2. Because the n is equal to 2 into 2, 4 plus 1, 5 lambda by 2. Therefore, we require the sin theta or the theta is equal to 5 lambda upon 2d. phi lambda upon 2d. All values are given. Therefore, angular distance theta is equal to phi into 10 raised to minus 7 upon 2. And d is given 0.01. Therefore, 12.5 into 10 raised to minus 3. Therefore, 0.0125 radian. Again, we is numerical here. In Young's, in front of a deflection by a single slit, the width of the slit is given. D is given as the 0.01 centimeter. The wavelength of light incident normally is 5000 angstrom. The angular distance of second maxima from the midline of a central maxima is how much radian? For that purpose, we are using the condition for nth order maxima. D sin theta is equal to 2n plus 1 into lambda by 2. Here second order maxima is given, therefore n is equal to 2. Therefore d sin theta is equal to 5 lambda by 2. We require the sin theta or the theta. Therefore sin theta is equal to approximate theta, angular width is equal to 5 lambda upon 2d. Okay. Now we substitute the wavelength lambda and also value of d. Therefore theta is equal to 5 into 10 raised to minus 7 upon 2 into 0.01. So we obtain the 12.5 into 10 raised to minus 3. That means 0.0125 radian. Clear this? Okay. Now after that, the question is asked in 2017. In Young's double slit experiment, if distance between the two slits is equal to the wavelength of light, d is given as the lambda, then the maximum number of black fringes obtained on the screen will be, how many numbers of the black fringes are obtained? So here we require the numbers of the black fringes, therefore we are using the condition for black fringes. Condition for the black fringes, there is the d sin theta is equal to lambda. But here d is given as the lambda. Therefore, lambda sin theta is equal to lambda. Lambda cancel. So here the n lambda sorry. Therefore n. Now we know that, but sin theta is less than or is equal to 1, and hence the n is also less than or is equal to 1. Therefore, the possible value of n are minus 1, 0 and 1. Therefore, 3 black fringes are obtained. 3 black fringes are obtained, corresponding to the one on either side of central maxima, corresponding to the 0 central maxima. Therefore, the 3 black fringes central maxima and first order maxima on either side of central maxima. This way, the 3 black fringes are obtained. Again, the width of a slit is equal to the wavelength of light used. So, how many maximum number of black fringes are obtained? For that purpose, here the condition for the black fringes d sin theta is equal to n lambda. D is given lambda. Lambda cancel. Therefore, sin theta is equal to n. Okay. But we know that the sin theta has the value is less than or is equal to 1. Therefore, n is equal to less than or is equal to 1. Therefore, the possible value of n are minus 1, 0 and 1. Therefore, the 3 black fringes are obtained. Okay friends, After that, next question that is asked in 2017, that is depends on the angular resolution of telescope. If the wavelength of light used is 6,000 angstrom, the angular resolution of telescope of objective lens having the diameter is 10 centimeter is how much radian? For that purpose, the wavelength is given, lambda is equal to 6,000 angstrom is given. Therefore, 6 into 10 is to minus 7 meter. Here the 10 centimeter width diameter is given, 10 centimeter. So it's equal to 0.1 meter. 0.1. What is the angular resolution? Alpha minimum. We know that the angular resolution for telescope alpha minimum is equal to 1.22 lambda upon capital D. 1.22 lambda upon capital D. Substitute the value 1.22 lambda 6 into 10 is to minus 7 upon D 0.1. Therefore 7.32 into 10 is to minus 6. That much radian. Where is it given? Already given, depends on the equation of angular resolution of a telescope. Here, if the wavelength of the light used is given the 6,000 angstrom, the angular resolution of a telescope of objective lens having diameter is 10 centimeter. So we know that the angular resolution of telescope is alpha minimum is equal to 1.22 lambda upon capital D. Substitute the value, we obtain the angular resolution is 7.32 into 10 is to minus 6. Now next question is maths column 1 and column 2. That is asked in 2018. Generally this type of the question are asked in Neet exam. But in 2018, so this type of the question also asked in good set. Here one side, here the physical phenomena are given. Here corresponding to that, what are the equation or the relation are given in column 2. We need to match it. In column 1, interference, Brewster's law, Malus law, and total internal reflection are given. In column 2, coherent sources, mu is equal to 1 upon sin c, and third is mu is equal to 10 theta p, and fifth is S is I is equal to I0 cos square theta. So here the two questions are there, two options are is Malus law, mu is equal to 10 theta p. Total internal reflection, mu is equal to 1 upon sin c. Effective index is equal to 1 upon sin c, critical angle. Right. Here the confusion about the coherent sources and I is equal to I0 cos square theta. Clear this? For that purpose, here options are given like this way: 1 with P, 3 with S, this way. So here the knowledge of our theory, we know that interference is coherent sources is required. Brewster's law, I is equal to 10 theta P. Now third, Malus law, I is equal to I0 cos square theta. And total internal reflection, that is the Q, mu is equal to 1 upon sin c. Again, with interference, here the option is coherent sources is required for interference pattern. Now Brewster's law. For Brewster's law, I is equal to mu 10 theta. Mu is equal to 10 theta p. Here R. Now for Malus law gives the intensity of polarized light. Therefore I is equal to I0 cos square theta. So here the S. And total internal reflection, here our answer is the mu is equal to 1 upon sin C. Therefore, our B option is right, 1 with P, 2 with R, 3 with S, and 4 with Q. Clear this? So very easy, but the knowledge, deep knowledge is required of all theory. Now next, which of the following is wrong for interference fringes? Also asked in 2018. So here the four options are given. Which is right? Which is wrong for interference fringes? First, the fringes are due to limited portion of the wavefront. Second option, all bad fringes are equally bad. Only because that in interference pattern, the fringes obtained having the equal intensity and equal separation. Option C, distance between the two consecutive bad fringes is constant. That is also right, that is also right. Now fourth, fringes are due to the use of coherent sources. Just we discussed about that in interference pattern. Here the coherent sources are required. Therefore, in interference fringes are obtained due to the coherent sources. So B, C, D are right, A is wrong. Therefore, the correct answer is A. The fringes are due to limited portion of the wavefront. Actually, here in interference pattern, the two waves are superposed on each other. Therefore, the entire wave is superposed on other wave. And as a result, due to the path difference, on the screen, the bright and dark fringes are obtained. Here, not limited portion of the wavefront are used. Entire wavefront is used due in superposition. While in diffraction phenomena, diffraction fringes are obtained only due to the diffraction portion of a wavefront. Diffraction portion of a wavefront. Because in diffraction pattern, according to the width of a slit, the wave is sparse, that means the wavefront is sparse. If the width is very small, therefore the small wavefront of the wave is sparse, therefore the diffraction fringes are due to the limited portion of the wavefront, while the interference fringes are not due to the limited portion of wavefront. Clear this? Okay. So B, C, D are the right sentences for diffraction fringes, interference fringes. We have to find out which is wrong. Therefore, first option is wrong. The fringes are due to the limited portion of wavefront. In interference fringes, the entire wavefront is superposed on other wavefront, and as a result, the interference fringes are obtained. Therefore, option A is wrong. Now, next is a ray of light traveling to impure water is incident on a glass plate is immersed in it. When an angle of incidence is 51 degrees, the reflected ray is totally plane polarized. The effective index of impure water is 1.4. The effective index of a glass plate is. Now listen here, what is given? The effective index of impure water is given the 1.4. We require the effective index of a glass plate. Right? Here the one wave is traveling from water into the glass plate. Traveling from water and enter to the glass plate. Here we need to find out what is the effective index of a glass plate. Here, whatever the light is incident on a glass plate, there is the reflected. This reflected light is plane polarized. Therefore, we are using the law of polarization, Booster's law. So, N is equal to tan theta P. N is equal to tan theta. Now, tan theta P is given already, tan 51. Therefore, N is equal to 1.235. Now, this thing is the effective index of a glass with respect to water. Therefore, N is equal to Ng upon Nw. Therefore, Ng is equal to N into Nw. N already we obtained 1.235. The effective index of a water is given 1.4. Therefore, we obtain the 1.729. That is approximate 1.7. Again here, ray of light traveling to impure water is incident on a glass plate immersed in it. When the angle of incidence is 51 degree, the reflected ray is totally plane polarized. The effect index of the impure water is 1.4. The effective index of a glass plane is. Here, what is given? The reflected ray is totally plane polarized. Therefore, we are using the Brewster's law. Here, the angle of incidence is given 51 degree. Therefore, mu or the n is equal to tan theta p. Theta p is 51. Therefore, tan 51. Tan 51 value is given 1.235. Thus, we obtain the effect index of a medium with respect to here impure water because the glass is immersed in water. Therefore, n is equal to mg upon nw. We require the effective index of a glass. Therefore, mg is equal to n into nw. Substitute the value, we obtain the 1.7. After that, the next, in Young's double slit experiment, the distance between the two slits is made 3 times than the fringe width. 3 times, then the fringe width will become small. Now here, in Young's double slit experiment, we increase the width of a slit. So, what should be the width of the fringes obtained on the scale? We know that the width of the fringes beta is equal to lambda capital D upon small d, and new width beta dash is equal to lambda D upon D dash. Now D dash is the new width of a slit, that is the 3 times of earlier. Therefore, beta dash is equal to lambda D upon 3D, but this is equal to beta. Therefore, beta upon 3. Therefore, 1 by 3 times fringes of the width obtained. One by beta. Only we have to use the distance between the consecutive bad fringes. Or the width of the bad fringes is beta is equal to lambda D upon D. Here only the small d we increase. Therefore, the new width of the fringes beta dash is equal to lambda D upon D dash. Here D dash is equal to 3D. Therefore, B dash is equal to lambda D upon 3D. Lambda capital D upon small d is equal to our beta. Therefore, beta upon 3D. Therefore, 1.3 times fringes of the width increases. Clear? Okay, here the most of the objective questions of this chapter are complete. Clear?